Okay, so now that we've talked about what Laplace transforms are, how to evaluate them, and how to do some math kinds of problems and partial fraction expansion with them, we're now at a point where we want to use Laplace transforms in circuit analysis. Now, just to remind you here, we had drawn this figure up several lessons ago. We have, a circuit, and we're wanting to get to my transient plus steady state response. And remember, if we're going down this path here, we have a differential equation that we need to solve, not e.g. EQ. So we have a differential equation we have to solve. We're going to go from a circuit to a transient and steady state. And we said, well, we'd like to have a path that doesn't require solving a differential equation. So what we do here is we do a Laplace transform, and so we get this in S domain. So this is Laplace transform. And then we get what I will call S domain solution. And this is using algebra to get to that S domain solution. And then we get back here, we do an inverse Laplace to get back to the transient and steady state. Now, this is, again, we kind of put this picture up here, but I want to talk about a little bit more what's going on here with this diagram here. So in this path here, if we just look up at this that we're looking at here, this is what we would call is time domain analysis, meaning that we're analyzing the circuit in the time domain with respect to time. Okay? Now, you might say, okay, well here, this is clearly, of course, S domain analysis, right? And without going into all the mathematical theory on this here, there's a key thing here that we can basically be able to do, and we're going to use this in lessons, especially when we get down to analyzing filters, is that you can have S, you can set S equal to J times omega. And we should be familiar with J times omega, because if you think about my impedance for an inductor is J omega L, and the impedance for a capacitor is minus J over omega C, which again is 1 over J omega C. So we should be able to say, oh yeah, I'm used to seeing a J omega here. And we'll be able to set S equals J omega, but then let's think about what that means as far as our analysis goes. Omega is an angular frequency. In other words, its units are radians per second. And of course we can change it to hertz just by dividing by 2 pi. So what we're doing here is, when we're doing S domain analysis, what we're really doing is we're doing frequency domain analysis. So it's an interesting concept, is that we're basically taking the circuit, transforming it into the frequency domain, doing analysis, and then we're able to transform it back in the time domain to have both the transient and steady state. So it's kind of an interesting concept there. But that's really what's going on here with these Laplace transforms, is that we're looking at analyzing circuits in the frequency domain. Alright, so let's actually get into what this analysis entails here. So first off, we should look at Laplace transforms And remember, we're talking about frequency domain now of circuit elements. And so the Laplace transforms of the circuit elements, well, we just have to look at our voltage current relationships. So if we remember here for a resistor is really easy. We have, and I'm going to emphasize this is V at t, so voltage with respect to time is equal to resistance times a current with respect to time. So that's just the basic Ohm's law that we're used to. But now if I take a Laplace transform of both sides, we don't want to overthink this here. It's going to be relatively straightforward. Well, the Laplace transform of the voltage here, well, that's just going to be the voltage in the S domain. And now I have to think, R is the resistance, but that's just a constant. That doesn't change. And I is again just the current, so this would just be R times I at S. So in other words, what we're saying here is if we have a resistor here that's got a resistance of R, and we have plus minus V at t, and a current going through here. Let me make a little bit better arrow. And a current going through here of I at t, then in the Laplace domain, we just have a resistor still with a resistance of R. The voltage is now just plus minus V at S, and the current through it is just I at S. So nothing really happens with the resistor, which, shouldn't be too surprised about that. That's the same thing that happened when we talked about impedance and when we were looking at steady state. Okay, so now let's look at an inductor here. So an inductor, and the reason I'm going to look at the inductor next is it's a voltage current relationship, so it somewhat looks like an Ohm's law, and remind you here that the voltage with respect to time for an inductor is equal to L times the derivative of the current with respect to time. Okay, so we're going to do the same thing here, is we're going to look at this and take a Laplace transform of the entire thing. Okay, well if I do the Laplace transform of this, well, Laplace transform of the voltage is still just my voltage, so capital V at S. And then again, well, I've got this current L, so that's just L still, because that's just a number, that's a constant. But then wait, I've got a derivative of the current. And you should remember from our previous lessons, we talked about the Laplace transform of a derivative. And let's go back to the table here, and you can see here, let's find time derivative here, the very first one here. If you have a derivative, you get S times F at S, but minus the initial condition. So what we end up getting here is we have L times square bracket will do S I at S, because that's just the Laplace transform of the current, minus I at 0 minus. So that's what we end up getting here for this. So let's go ahead and kind of expand this out a little bit. So we have V at S is equal to S times L I at S minus L times I at 0 minus. So let's look at what the circuit looks like for this. So the circuit here in the time domain, we just have a capacitor, not a capacitor, an inductor, and we've got some voltage here, V at t, and then we've got current I at t, and we have some initial condition, and actually this shouldn't be capital I, this should be lowercase I. Not a huge deal, but it is technically lowercase I. And then we have an initial condition, I at 0 minus, and I'll just say that's equal to capital I sub 0. So it's some number. which obviously either we'd have to find or would be given to us. Okay, so this is the time domain, and then if we move this into the S domain, or the frequency, well, we still have the inductor, but now, and I should put here this is L, we have that this is S times L, because look at my voltage current relationship. I've got S times L, my current, so that's now S times L. I've got my voltage here, V at S, and then I've got my current, I at S. But I have something else here. Actually, I should give myself a little bit more space here. Because look what I have here. I've got an additional term here. Now, I have to think about what kind of term this is. Well, first off, I know the units of this, because let's just think about this for a second. Volts is on the left-hand side here. So, voltage has got units of volts. So we know that every term on the right-hand side has to have essential units of volts. So I've got minus L times I at 0 minus. So that's some kind of voltage. And so what we have here then is we actually have a voltage source, and you have to be a little bit careful. It's minus plus, and that's just because of the fact that we have a subtraction there. And then the value of this voltage source would be L times that initial current. And so this would actually be plus minus Vs, because it includes that initial condition. Alright, so that's an important thing we should look at. Now there is another way you can write this here. You can do a source transformation on this, and you can convert this to where you have an inductor, and it's still S, L at S, but it's going to be then in parallel with a current source, and the current source would be going down, and this current is going to be I sub 0 over S. And how do you get that it's I sub 0 over S? Well, you're literally looking at a source transformation here, so you would have I L I sub 0 divided by SL. And of course, the L's would cancel out, and you'd have I out over S. Now, this is again if we're giving some initial condition. But one thing else here we need to emphasize, this is extremely important. If I sub 0 equals 0, so initial condition is 0, then the time domain just goes to S times L V at S. And that's pretty easy to see if we think about this for a second. If I have no initial condition, in other words, if the initial condition is 0, I would have 0 times L, so this voltage source would be 0. In other words, the voltage source would be turned off, and we know when we turn off a voltage source it would be a short. And even if you look at it this way, I0 being 0, so this current supply would be 0, so the current source would be off, but when you turn a current source off it would act as an open, and so you'd be left with just the inductor. And that's important to know, because in a lot of the examples we're going to be looking at and a lot of the problems we're going to be doing in class are going to be where the initial conditions are just 0. Now in some cases we will have initial conditions, but hey, if the initial conditions are 0, that's easy. There's nothing really even hard. It just becomes the same circuit element. In this case it's S times L. Alright, well we have one more to look at here. I won't spend quite as much time going through this one as we did for the inductor here, but it's for, of course, the capacitor. And remember, for a capacitor, you have the current with respect to time is equal to the capacitance times the derivative of the voltage. So again, all we're going to do is a Laplace transform, and we're going to use that same derivative rule that we used in the previous case, but now this time we're going to get I at S is equal to C times S V at S minus my initial condition for my voltage. And now we are going to do a tiny bit of rewriting of this. So this would be S times C V at S minus V at 0 minus. Now I'm going to rewrite this and solve for V at S. You might say, why am I solving for V at S? Well, let's look back here. We're always wanting to have some kind of Ohm's law relationship. Voltage is equal to something times current. You know, and for the resistor, it's just, of course, R times the current. In the case of the inductor, it was just S times L times the current, and then, yeah, we had the initial condition. So I want to do the same thing for the capacitor, and I'm going to skip the steps of solving this. This is really easy to solve for V. So you get V at S is equal to 1 over S times C I at S plus, oops, there should be a C there, plus V at 0 minus over S. And so what that means for a capacitor is, in the S domain, the capacitor is going to look like the following. This is initial condition V naught. In other words, that's my initial condition at 0 over S, and then this would be 1 over S times C, which again, you could do a source transformation. And if you did a source transformation, making sure you're careful with the directions of everything, you would wind up with the following. And you'd get a current source. Now again, you need to be careful of the directions of these things, so if I want to make sure that we're careful here, this is plus minus V at S plus minus V at S, and the current, that would be I at S, and the current here would be I at S. So we're careful with all the signs and the directions. Now, just like with the inductor, if V0 equals 0, then the S domain capacitor is simply a capacitor with a value of 1 over S times C. Alright, this video has been a little bit longer. There's a couple more things I want to talk about regarding this, which we'll pick up at the beginning of the next video, and then we'll be able to, believe it or not, but we're going to be able to be ready to do circuit analysis.